Okay, so in this video, we want to consider a few other special types of limits, giving us slightly strange cases, and we'll see that using in these special cases the natural logarithmic function, we can then be able to use, we are then able to use, sorry, L'Hopital's rule. And these are the following special cases. There is 1 to the infinity case, there's infinity to the 0 case, and 0 to the 0 case. What they have in common is this rather strange exponent with respect to the base. And you'll see in each case we will take the ln of the limit, which will allow us to bring the exponent down every time, and then we will be able to turn this into a L'Hopital's rule type problem and solve the limit. We'll do an example in this video of this case and this case. I'll leave this case up to you whenever you encounter it. It works just the same way as these two other cases. And you'll see that these are very subtle cases, and you'll see with the answer that we will obtain from our first problem. Let's look at this limit. We're going to let x go to infinity. So 1 plus 1 over 2x to the power of x. So the limit looks deceptively simple, right? But let's look at what kind of case we get and realize that we have to be very careful. And the confirmation of this will be reached once we obtain the final answer of this limit. So look at the inside. We have a variable raised to a variable power. As x goes to infinity, 1 over 2x goes to 0. So we'll have a 1 plus 0 for the base, which will be approaching 1. And the exponent is x, and x approaches infinity. So we have a 1 to the infinity case. Now here's where you have to be careful. You don't want here to fall into the trap of saying, well, 1 to any number is always 1. So this has to be 1. It cannot be anything other than 1. And this is a huge mistake. Before we even attempt to figuring out the answer directly, let's try and think about why this is not so obvious. This is a case. This is an intuitive feeling for the limit. When we're saying 1 to the infinity, we're not saying that the base is exactly 1. We're saying it's roughly 1, and the power is very big. But look at this expression along the real line. You have the value 1, and the base of your expression, 1 plus 1 over 2x, is always slightly bigger than 1. As x approaches infinity, x is always positive. It may be large, but still positive. You'll have 1 over 2x, which will be very small, but still positive. So you'll have 1 plus a very small number. So I'll exaggerate here, but your base, your 1 plus 1 over 2x, is always strictly bigger than 1. Always. As x approaches infinity, 1 over 2x shrinks to 0. So this point will get closer and closer and closer to 1, but it will, for any positive value of x, always be strictly bigger than 1. Now think of what you have. You have the exponent of this term. So for any x, 1 plus 1 over 2x is a positive number that is bigger than 1. And now you take the power of this number to be x, but the power gets bigger and bigger and bigger. And so a large power of something bigger than 1 will naturally be getting bigger. So you have here two opposing forces. The 1 over 2x shrinking to 0 is trying to push the expression closer to 1, but the exponent, getting bigger and bigger and bigger, is trying to make this go to infinity, because this number is always bigger than 1, and a large power of something bigger than 1 will naturally be big. And so we have two opposing forces here. And it's really not clear what's going to happen? Let's now show that this is really not obvious by finding the answer. Let's call this limit L. We're trying to solve for L. We're trying to evaluate this limit. The idea is to ask yourself, why is this hard? Because of this rather bizarre case, namely being this bizarre exponent. In each case you have this strange exponent. If we could bring it down, we'd have a product, and then perhaps we could use L'Hopital's rule. Well, think of which function allows you to bring exponents down. That function is the natural logarithmic function, because the ln of a to the b is just b ln of a. So what we'll do here is we will find the ln of L, and then in the end solve for L. So the ln of L, well, L is the limit, so it's the ln of the limit The question is now, what can we do with this? Well, this is always strictly bigger than 1, and with the positive power, this will always be bigger than 1. And the ln, if you look back to the graph, is a continuous function for positive values. And because the ln is continuous, remember the property of continuous functions. A function of a limit is the limit of the function as long as the function is continuous. So by continuity of ln, we can interchange the function and the limit. So ln of the limit will simply be the limit of the ln of the expression. And now if you leave it like this, of course, you still won't get a proper case, but you can bring the exponent down and see what you get now. You have x times the ln of 1 plus 1 over 2x. Let's look at what case we have here. As x goes to infinity, x goes to infinity. As x goes to infinity for the second term, 1 over 2x will shrink to 0. And you'll be left with the ln of 1, but if you remember, the ln of 1 is 0. So we have an infinity times 0 case. And from this point on, we know how to proceed. We can send either term down, and then we'll be able to use L'Hopital's rule because we'll get either an infinity over infinity case or a 0 over 0 case. The rule of thumb is send the simpler term down, so we won't send the ln down, but we'll send the x down as a over 1 over x. So we'll have ln of 1 plus 2x on top, over 1 over x, because of course if you divide by x, that's the same as multiplying by x. And now what kind of case do we have? Well, 1 over 2x shrinks to 0, ln of 1 is 0, over, as x goes to infinity, 1 over x shrinks to 0, and now we have a 0 over 0 case. We can now use L'Hopital's rule. Differentiate the numerator, and be careful here to complete the chain rule. The derivative of the outside function is the derivative of ln, which is 1 over the argument, so 1 over 1 plus 1 over 2x, times the derivative of the argument. The derivative of 1 is 0, plus, and now here, rewrite the 1 over 2x as 1 half x to the negative 1. So if you differentiate this, you'll get negative 1 half x to the negative 2, which will be negative 1 over 2 x squared. This takes care of the derivative of the inside, which completes the derivative of the numerator, over the derivative of the denominator, As we have just said, 1 over x is just x to the negative 1. From the power rule, the derivative of this is negative x to the negative x to the negative 2, which you can write as negative 1 over x squared. But now think of it. You have on top a negative 1 over x squared, and on the bottom a negative 1 over x squared. You can cancel both of these. Don't cancel the 2. And look at what you're left with. You have 1 over 1 plus 1 over 2x times 1 over 2. And the limit here is simple enough that we can now let x approach infinity. As x goes to infinity, 2x goes to infinity, so 1 over 2x will shrink to 0. We'll have a 1 over 1 plus 0 case, which is just 1. So this approaches 1. So we'll have 1 times 1 half, which in the end gives us 1 half. And here's where you have to be careful. Don't leave 1 half as your final answer. Because what is 1 half equal to? Go back to the very beginning. We were trying to find this limit, which we called L. What we have found in 1 half is not L, but if you backtrack, it is the ln of L. But we wanted to find L, not the ln of L. Well, let's see what we have then. The ln of the limit is equal to 1 half. The question is, how do we solve for the limit L? Because the original question was to find the limit, not the ln of the limit. Well, if you think of it, that means that we have to cancel the natural logarithmic function, therefore the logarithmic function base e. Well, which function would allow you to solve for or cancel ln, that is its inverse function, being the natural exponential function, so the exponential function base e. Right? Remember that the ln is the inverse of e, so ln of e to the x is just x. Ln cancels e to give you back the argument, and it works in the same way if you compose in the opposite order. E to the ln of x, ln is the inverse of e, being the inverse of a function is symmetric, so e is the inverse of ln. E cancels ln and gives you back x. If you want to cancel the ln, you have to raise it to the natural exponential e. Let's do this now. Both sides are equal, so e to the left-hand side, so e to the ln of L equals, and now make the substitution. Ln of L we know is 1 half, so replace ln of L by 1 half, and you'll have e to the 1 half. Well, e is the inverse of ln, so e and ln cancel each other out, and you're left now with L, the limit, is actually e to the 1 half. If you want, you can write the power of 1 half as the square root, so the limit is the square root of the number e. And that's really not obvious. I mean, think back to what we had as a case. We said what happens to 1 over 1 plus 1 over 2x to the x as x goes to infinity. We had this bizarre case of 1 to the infinity, and you see that in the end, the answer is the square root of e, which is approximately 2.71828. And that's clearly not equal to 1. So as you see, you have to be very careful with 1 to the infinity cases. A case like this could end up being anything. And in this case, surprisingly, it ends up being the square root of e. So always be careful. Don't jump to the conclusion and thinking, well, 1 to any number is 1, the limit has to be 1. That's not true. Because what we have as a base is not exactly 1. It's close to 1, but not exactly. And infinity is not a number, it's just to say that the exponent of our expression is getting bigger and bigger and bigger. So a case like this can be literally anything, and you have an example of this right here. And always be careful, every time you take the ln of a limit, when you then are able to use L'Hopital's rule and find the answer, always think back that what you have found is not the limit itself, but the ln of the limit. And so to isolate back the limit, the original problem, exponentiate both sides with a natural base e. This allows you to cancel the ln, and then you get to solve for the original limit. And that's how you handle a case of the type 1 to the infinity. And these other cases are handled the same way. If you had an infinity to the 0 case, or a 0 to the 0 case, you do the same thing, take the ln, clean it up, so you can then use L'Hopital's rule, and in the end exponentiate both sides, so you can solve for the original limit. Let's do one more example. We'll do an example of this type of cases, and then I'll leave this case up to you, because at that point it becomes just redundant. And this will be, for the videos, our last example of L'Hopital's rule. With this, you'll be able to solve practically any limit that requires the use of L'Hopital's rule. So here's the problem. We are letting x approach infinity. Considering now x squared plus 1 to the power of 1 over x. As always, look at the case that you have. As x goes to infinity, x squared plus 1 goes to infinity. So the base of our expression gets bigger and bigger and bigger, but the exponent is 1 over x. As x goes to infinity, 1 over x goes to 0. So we have an infinity to the 0 case, and that is again a rather non-obvious case. Because think of it, the base is getting bigger and bigger and bigger, so it's trying to push off the expression to infinity, but the power is getting closer and closer to 0. And if you take a positive real number to the power 0, that's equal to 1. So there are again here two opposing forces. The base is trying to make the expression bigger and bigger and bigger, but because the power is getting closer to 0, it's trying to bring back the expression closer to 1. The question is, which term is going to win? Is it the base that will blow this up to infinity? Is the power going to bring it back down closer to 1? Or maybe they'll balance each other out to some positive number. Anything could happen. So let's see now. Again, we have a case with a bizarre exponent, so we will call this limit L, and with the help of the ln function, we'll be able to solve this problem. Ln of L equals the ln of the limit. As we have said before, what we have is positive. The ln is a continuous function on the positive real line. So the ln of the limit will be the limit of the ln. Now we use our property of the logarithmic function. Ln of a to the b is b ln of a. We can move the exponent outside as a multiple of the ln of the base, which will give us the limit as x goes to infinity of 1 over x times the ln of x squared plus 1. Well, if we want to use L'Hopital's rule, we have to have a single fraction, but multiplying by 1 over x is just dividing by x. So we'll have the ln of x squared plus 1 over x. Let's look at our case. As x goes to infinity, so does x squared plus 1, but the ln of something which goes to infinity also goes to infinity. If you remember, this is the graph of e to the x, this is the graph of ln of x. And as x goes to infinity, ln of x also will go slowly, but it will get bigger and bigger and bigger. It will go to infinity. So you have an infinity over, well, this is just redundant as x goes to infinity. x goes to infinity. So we'll have an infinity over infinity case, and now we can use L'Hopital's rule. We apply L'Hopital's rule. The limit as always stays the same. Differentiate top and bottom. The derivative of the numerator, well, ln is the outside function. The derivative of ln is 1 over the argument, x squared plus 1, chain rule, times the derivative of the argument, which is 2x, and that's the derivative of the numerator, and we divide this by the derivative of the denominator, but the derivative of x is simply 1. So if you divide something by 1, you get back the same thing. Well, let's write this as a single fraction. So we get the limit, as x approaches infinity, of 2x over x squared plus 1. Now here we have two options. As x goes to infinity, we have an infinity over infinity case. We could use L'Hopital's rule, which will give us the limit in one step, or we could realize that what we have is a ratio of two polynomials. So we could simply divide top and bottom by either the larger power of x on top or on the bottom. This will also give us a one-line solution. I'll choose here to divide top and bottom by x squared. If you divide top and bottom by x, you'll get to the same thing. If I do 1 over x squared times 1 over x squared, then if you choose to use L'Hopital's rule, it will be equally simple, even actually a little simpler. And what are we going to get? X over x squared is 1 over x, so we get 2 over x on top, over x squared over x squared is just 1, plus 1 over x squared. And now as x goes to infinity, 2x shrinks to 0, 1 over x squared shrinks to 0. So what we have is a 0 over 1 case. But 0 over 1, that's just equal to 0. And you would have arrived at the same answer if you had used, also in one line, if you had used instead of this trick, L'Hopital's rule for this term. And now we're done, but again, remember that what we have found is not the original limit. We were trying to solve for this limit, therefore L, but we had to use a ln of L to allow us to use L'Hopital's rule. So now, as we had in the first problem, 0 is not equal to L, but 0 is equal to the ln of L. So, the ln of the limit equals 0. As we did before, to cancel the ln, we must exponentiate both sides with a natural base. So e to the ln of L is e to the 0. E cancels with ln. Therefore, L, the limit, is e to the 0, but any positive real number to the 0 is equal to 1. And you see that the limit is equal to 1. So if you go back to the case that we had, so as x goes to infinity, x squared plus 1 to the power of 1 over x will be equal to 1 in the limit. And you see that the term that took over here, that 1, was the power of 0. The power of 0 brought this down to a value that is closer and closer and closer to 1, because the limit, as we can see, is equal to 1. In other cases, as we have discussed previously, the infinity could have taken over and gave us a limit that was infinite. And if they're roughly of the same magnitude, we could have ended up also with any positive real number. When you have a case like this, as the other indeterminate cases, anything goes. And here we had a limit of 1. And as I said before, if you add a 0 to the 0 case, do the same thing, take the ln, and then find the limit with L'Hopital's rule. In the end, don't forget that what you have is the ln of the limit, so exponentiate and solve for the original limit. And you see why this is also an indeterminate case, because if the base shrinks to 0, it's trying to make the whole expression becomes smaller and smaller and smaller. So it's pulling the expression closer to 0. But with a power of 0, any positive number to the 0th power is 1. So then the other part of the expression, the 0, is trying to pull the expression closer to 1. So once again, you have two opposing forces. The base shrinking to 0 is trying to make the expression approach 0. The power approaching 0 is trying to make the whole thing approach 1. So once again, when you have a case like this, you could have a lot of different final answers. And with this now, the idea of in a case like this, or like this, or like this, taking the ln will then allow you to solve for the ln of the limit using L'Hopital's rule. And with this, you're now ready to solve every problem on the problem sheet on L'Hopital's rule.